When nearly every automaker on Earth rushed to declare the internal combustion engine dead, and Wall Street kept calling Toyota an outdated dinosaur standing on the edge of obsolescence, hardly anyone stopped to ask the one question that actually matters. Why would the #1 automaker on the planet risk its entire legacy by going against the tide? The answer just came out of Yamaha's workshop, the same partner that helped build the legendary Lexus LFA. A naturally aspirated 5-liter V8, 450 horsepower, burning pure hydrogen and emitting nothing but water vapor. But the real story isn't the horsepower number, it's what's hiding behind those 8 cylinders. A calculated blueprint for bringing clean, gasoline-like driving to everyday people. 3-minute refueling, decades of mechanical life, and zero dependence on a battery pack that quietly ages out from under you. Because here's the dilemma nobody wants to say out loud. You want to do right by the planet, but you also don't want to sit in a charging line in February watching your range evaporate. And you definitely don't want a $50,000 car that loses half its value at the moment the battery fades. Toyota and Yamaha believe they've finally engineered a third way. Let's break it down.
The Multi-Pathways Plan. By the mid-2020s, the writing was on the wall almost everywhere you looked. The European Union set a 2035 deadline to end sales of new fossil fuel cars. The UK and a growing list of US states drew similar lines in the sand. Hundreds of billions of dollars poured into lithium-ion gigafactories, and the message from regulators, investors, and most of the industry was blunt. Battery electric is the only road to zero emissions, and everything else is a distraction. Toyota didn't fall in line, and it paid for that publicly. Under then-CEO Akio Toyoda, the company took years of criticism for refusing to go all in on EVs, with headlines painting Toyota as a company clinging to the past while the rest of the world moved on. Analysts questioned the stock, competitors leaned hard into the contrast. For a company that built its reputation on reading the market correctly, the same company that made the Prius mainstream when hybrids were still a punchline, that was not a comfortable position to be in. Toyota's answer was consistent. Carbon is the enemy, not the internal combustion engine. It sounds like a slogan, but it's actually a pointed rebuttal to a narrative that treats every driver on Earth as if they live in the same house, with the same garage, the same stable power grid, and the same mild climate. Millions of people don't. Apartment dwellers without home charging, rural drivers hours from the nearest fast charger, regions where the grid itself can barely keep the lights on, let alone fast charge a fleet of SUVs. The hydrogen V8 is Toyota and Yamaha's way of putting a stake in the ground. Zero carbon driving doesn't have to mean abandoning everything mechanical engineers have spent a century perfecting. It's proof in physical, drivable form that zero emissions and internal combustion aren't automatically opposites. They're only opposites if you insist there's just one way to get there.
Inside the 450 HP V8, the engine didn't come from a blank sheet of paper. It's built on Toyota's proven 2UR GSE, the naturally aspirated 5.0-liter V8 that's powered the Lexus RCF, GSF, and LC. Yamaha didn't design that engine from scratch either, which is exactly the point. This is a company with a track record here, from co-developing engines with Toyota going back to the 2000 GT to shaping the screaming V10 heart of the Lexus LFA. When it comes to making an engine sing, Yamaha has done this before. Swapping gasoline for hydrogen isn't a simple fuel change. It's a different kind of fire entirely. Hydrogen burns roughly 8 times faster than gasoline, which gives you an almost instantaneous throttle response, but it also comes with real risk, pre-ignition, backfiring, and combustion temperatures that can chew through components built for a slower burning fuel.
To handle that, Yamaha rebuilt the engine's core systems. New high-pressure direct injectors, engineered specifically to meter gaseous hydrogen instead of liquid fuel. Redesigned cylinder heads, reinforced intake manifolds, new intake valves and piston crowns shaped to survive a completely different thermal cycle. Then there's the exhaust, and this is where the engineering gets almost theatrical. Yamaha routed the exhaust runners upward into a top-mounted 8-into-1 collector, producing a high-frequency race car-like note that sounds like nothing else on the road, while the only thing actually leaving the tailpipe is condensed water. The numbers Yamaha has published, 450 horsepower at 6,800 RPM and 398 pounds-foot of torque at 3,600 RPM. Figures that land remarkably close to the gasoline version of the same engine. That's the part that should stop you for a second. Engineers didn't just make hydrogen combustion work, they made it work without gutting the performance that made this engine desirable in the first place. This isn't a compromised, watered-down substitute you tolerate for the sake of the planet. On paper, it drives like the V8 it was born from.
Why a V8 first? Here's a fair question. If the real goal is putting clean technology into ordinary family cars, why start by building a high-strung V8? Because a race engine is a stress test with a steering wheel attached. Push a powertrain to its thermal and mechanical limits, the red line, the track, the punishing heat cycles, and you learn everything that can go wrong before it ever reaches a customer's driveway. It's the same logic behind Formula One tech eventually trickling into road cars, and the same logic that shaped the Lexus LFA before it. A 450 horsepower hydrogen V8 revving to nearly 7,000 RPM is Toyota and Yamaha's storm test, and everything learned here about injector wear and thermal stress becomes the foundation for a version that has to be boring, reliable, and cheap to fix in a family sedan.
Fixing EV headaches. Ask any EV owner what they'd change, and two answers come up constantly: how long it takes to refuel and how long the car itself is realistically expected to last. On refueling, high-pressure hydrogen dispensing at 700 bar can bring a tank to full in roughly 3 to 5 minutes, basically a gas station stop. Compare that to a best-case DC fast charge, which still runs 30 to 45 minutes under ideal conditions. And ideal conditions is doing a lot of work in that sentence. Cold winter weather alone can slow charging dramatically and cut usable range by a meaningful margin, on top of the very real, very common experience of pulling up to a charging station only to find every stall occupied or a payment terminal that simply doesn't work. Then there's the ownership question nobody likes to talk about at the dealership. What happens to the battery after year 8, 9, 10? Battery chemistry degrades over time, and once a pack falls out of warranty, replacement costs can run into the 5-figure range, in some cases high enough to exceed what the used car is even worth on the market. That's not a hypothetical, it's a math problem that's already showing up in used EV pricing. A hydrogen combustion engine, by contrast, is still fundamentally a metal engine. Cast components, machined parts, a mechanical architecture with a track record stretching back over a century. These are systems that, properly maintained, can realistically run for 15, 20, even 25+ years. And when something does wear out, an injector, a valve, a bearing, it can be rebuilt or replaced at a normal repair shop, not scrapped as a total loss because one expensive component failed. A dead battery pack often means the car itself is functionally dead. A worn valve is a Tuesday afternoon at a garage down the street. From track to street. This isn't theoretical. Toyota has already been running hydrogen combustion in actual competition. The GR Corolla H2 has raced in Japan's Super Taikyu Endurance Series, with Akio Toyoda himself getting behind the wheel under his Morizo Racing alias to personally evaluate it. The GR Yaris H2 has been demonstrated on public roads in Europe, including a run at the WRC in Belgium. And Toyota has shown a Corolla Cross H2 concept, a 5-passenger crossover running a hydrogen version of the same 1.6-liter turbocharged 3-cylinder used in the GR Corolla, built using tank technology borrowed from the Mirai fuel cell sedan. Over successive racing seasons, Toyota has reported real, measurable gains, double-digit increases in hydrogen combustion power and torque, closing the gap toward gasoline engine performance. That's the trickle-down pipeline in action. V8 Halo project on one end, everyday nameplates like the Corolla, RAV4, Camry, and Hilux as the eventual destination on the other. None of this is finished technology sitting on a showroom floor. Toyota itself has been upfront that hydrogen combustion isn't yet ready for full commercialization. But every endurance race, every mechanical failure discovered under pressure is a data point pulling this closer to something you could actually buy.
Saving 1.4 billion gas cars. Here's a number that rarely makes it into the EV conversation. There are roughly 1.4 billion internal combustion vehicles currently on the world's roads. Scrapping all of them and replacing every single one with a new EV isn't just expensive, it comes with its own enormous manufacturing carbon footprint before the replacement car has driven a single mile. Because hydrogen combustion shares the overwhelming majority of its fundamental architecture with a standard gasoline engine, same basic block, same core mechanical principles, it opens the door to something EVs structurally can't offer: conversion. Modified injectors, an adapted ECU, a hydrogen tank. In theory, that's a path to turning an existing car into a zero-emissions vehicle without buying a new one at all. It's early, it's not commercially available yet, but it's a fundamentally different strategy than buy new or keep polluting. Compare that to a battery EV, which is engineered from the ground up around a completely different platform, a completely different set of components, and a battery pack that simply cannot be retrofitted into a car designed decades ago for a fuel tank and a crankshaft. If the ultimate goal is cutting global emissions as fast as possible, a strategy that could theoretically touch a meaningful slice of that 1.4 billion car fleet deserves serious attention, not dismissal.
Swappable cartridges. The obvious pushback on all of this: hydrogen infrastructure is expensive. A full-scale 700-bar hydrogen filling station can cost well over $1 million to build. You can't out-argue that. It's real, and it's the single biggest obstacle hydrogen has faced for years. But Toyota's answer isn't necessarily build more of those. Through its Woven Planet subsidiary, Toyota has already shown a working prototype of a portable, swappable hydrogen cartridge, a compact cylinder, roughly the size of a small fire extinguisher, designed to be swapped out much like a propane tank rather than pumped from a fixed station. The idea is to sidestep the need for a massive pipeline of dedicated hydrogen stations by making hydrogen something that can be delivered, restocked, and exchanged the way propane tanks already are at hardware stores and gas stations across the country. It doesn't solve every infrastructure question overnight, but it reframes the problem from build an entirely new national network from scratch to distribute a product people already know how to swap.
The hard truths. Now, to truly understand whether this technology can conquer the mainstream, we have to look directly at the immense engineering hurdles Toyota and Yamaha had to confront. Because burning hydrogen in a piston engine isn't just a matter of changing the fuel tank, it rewrites the rules of thermodynamics. First is the emission question. While pure hydrogen combustion produces zero carbon dioxide, burning it at extreme cylinder temperatures introduces a different byproduct, nitrogen oxides, or NOx. When hydrogen ignites inside a combustion chamber, the intense heat forces the nitrogen and oxygen in atmospheric air to bond together.
Toyota and Yamaha anticipated this from day one. To eliminate NOx without choking power, engineers implemented ultra-precise water injection systems and advanced lean burn combustion mapping, paired with specialized catalytic aftertreatment. The result is an engine that satisfies strict zero-carbon standards, but it requires sophisticated thermal management that standard gasoline engines never had to deal with. Then there is the unavoidable math of thermal efficiency. A modern battery EV converts roughly 75 to 85% of the electrical energy drawn from the grid directly into wheel rotation. By contrast, an internal combustion engine burning hydrogen operates at around 25 to 30% thermal efficiency, with the remainder dissipated as heat. For EV advocates, this is the core criticism. Powering a fleet of hydrogen combustion cars requires significantly more upstream renewable energy than charging batteries directly. But Toyota's counterargument looks at the total system. Hydrogen can be produced from surplus renewable power that would otherwise be curtailed, stored indefinitely without degrading, and transported without overloading local electrical grids during peak hours.
The ambition to retrofit the world's 1.4 billion gasoline cars also faces physical constraints. Swapping fuel injectors, adjusting ignition timing, and remapping an ECU are relatively straightforward mechanical tasks. The true challenge lies in fuel storage. A 700-bar hydrogen tank is not a stamped steel container. It is a thick, carbon fiber-wrapped composite pressure vessel built to withstand violent collisions. Integrating these rigid cylindrical tanks into passenger vehicle chassis that were never designed for them requires ingenious packaging and crash structure re-engineering. Even modular swappable cartridges represent an evolving stepping stone rather than an overnight fix. A single portable cartridge holds several hundred grams of hydrogen, perfect for short urban hops, commercial delivery fleets, or range-extending backups, but scaling up to 300 miles of highway range still demands multiple interconnected canisters. None of these realities diminish what Toyota and Yamaha have achieved. Instead, they highlight why this project is so monumental. The Japanese alliance isn't pretending these obstacles don't exist. They are actively road testing, racing, and engineering their way through them.
Jobs and driver freedom. There's a bigger, quieter story running underneath all of this. Who controls the supply chain for your next car? A large majority of the world's lithium refining, cobalt processing, and battery cell manufacturing capacity is concentrated in China. That's not a criticism of any one country. It's simply a fact about where today's battery supply chain is built. A hydrogen combustion engine sidesteps that dependency almost entirely, running instead on standard steel, aluminum, and manufacturing tooling that's been in place for decades, rather than materials tied to a handful of geographically concentrated mines and refineries. There's also a jobs story here. A battery electric vehicle typically has significantly fewer moving parts than a comparable gasoline car, which sounds efficient until you consider what that means for the millions of people whose jobs involve machining, casting, and assembling those now unnecessary components across Japan, North America, and Europe. Keeping a mechanical ecosystem alive also keeps independent garages in business, the neighborhood mechanic who can fix your car, instead of a future where only the manufacturer's dealership can touch a software-locked EV.
The final verdict. So where does that leave us? None of this means the Toyota Yamaha Hydrogen V8 is trying to kill the electric vehicle. It's not a rejection of where the industry is heading. It's an argument for keeping more than one road open. Battery EVs make enormous sense for dense city driving and predictable daily commutes, but long-haul travel, sports cars, heavy-duty trucks, and budget-conscious drivers who can't gamble on a battery replacement bill down the road, that's exactly the space where hydrogen combustion is trying to carve out its future. The bigger promise buried in all of this is almost emotional. The sound, the feel, the mechanical connection that made people fall in love with cars in the first place doesn't have to be sacrificed to save the planet. That's the bet Toyota and Yamaha are making with this engine, even knowing the efficiency math, the NOx question, and the packaging problem are still unsolved. Whether hydrogen combustion actually scales to the mainstream the way Toyota hopes is still an open question, but for the first time in years, there's a serious, well-funded, mechanically proven alternative to batteries or nothing, and that alone changes the conversation. If you don't want to miss where this story goes next, because Toyota is nowhere near finished with this idea, hit subscribe now so the next video lands in your feed automatically. Now, here's the question I want you to fight about in the comments. If you could walk into a dealership a few years from now and buy a hydrogen-powered car with zero emissions, a 3-minute fill-up, and a proven 20-year lifespan for the exact same price as a regular gas car, would you actually choose it over a battery EV? Or is range anxiety already a habit you can't shake? Drop your answer below, and I'll see you in the next one, where we're going to break down exactly why hydrogen stations have been so expensive to build and whether that's about to change.